Hello and welcome. Before we begin this gentle journey through the cosmos, if you enjoy calm, scientific explorations that help you relax or drift into sleep, please consider subscribing to the channel and leaving a like. It helps others find this peaceful space too. Now, let's softly turn our attention upward toward 3 points of light that have watched over humanity for thousands of years. The 3 stars we call a belt. When you look up at the night sky on a clear winter evening, you might notice 3 stars arranged in a nearly perfect line. These stars form what we call Orion's belt. They shine with steady brightness, visible from almost anywhere on Earth. People have watched these stars for thousands of years, telling stories about them, using them for navigation, and wondering what they might be. But these aren't just points of light painted on the sky. Each one is an enormous sun, much larger than our own, burning with tremendous energy across vast distances. They appear close together from our perspective here on Earth, but in reality, they are separated by dozens of light years. They don't actually form a physical group in space. They simply happen to align along our line of sight, creating this beautiful, recognizable pattern. The 3 stars have names given to them long ago. The leftmost star, as we see it from Earth, is called Alnitak. The middle star is Alnilam, and the rightmost star is Mintaka. These names come from Arabic, reflecting centuries of astronomical tradition. Each name carries meaning related to position or appearance, reminders of how humans have always sought to understand and organize the heavens. Alnitak, Alnilam, and Mintaka are all blue supergiants. This means they are exceptionally large, exceptionally hot, and exceptionally bright. Their surfaces glow with temperatures far higher than our sun's. While our sun's surface sits around 5,700 degrees Celsius, these stars burn at temperatures exceeding 20,000 degrees or more. This extreme heat gives them their characteristic blue-white color. Blue stars are rare compared to cooler, redder stars. They represent a brief but spectacular phase in stellar evolution. Stars this massive burn through their nuclear fuel much faster than smaller stars. While our sun will shine for about 10 billion years in total, stars like those in Orion's belt might last only 10 or 20 million years before they exhaust their fuel and end their lives in dramatic supernova explosions. But we're getting ahead of ourselves. Let's slow down and look at each star individually, understanding what makes it unique, what scientists have measured about it, and what role it plays in the larger cosmic landscape. Alnitak sits at the eastern end of the belt, lowest on the horizon as the constellation rises. Its name means the girdle in Arabic. At a distance of roughly 815 light-years from Earth, Alnitak is actually not one star, but a triple star system. Through powerful telescopes, astronomers have identified 3 distinct stars orbiting each other in a complex gravitational dance. The primary star, Alnitak A, is a blue supergiant with a mass approximately 33 times that of our Sun. Its diameter spans about 20 times our Sun's width. If you could place Alnitak A where our Sun sits, its surface would extend well beyond the orbit of Mercury, possibly reaching Venus. This star produces light with astonishing intensity. It shines with a luminosity roughly 120,000 times greater than our Sun. This means that in every second, Alnitak A radiates 120,000 times more energy into space than our home star does. Despite being more than 800 light-years away, it appears as one of the brighter stars in our sky, a testament to its tremendous output. Alnitak A has a companion, Alnitak B,
orbiting it at a distance of about 3 times the span between our Sun and Earth. Alnitak b is also a blue supergiant, though somewhat smaller and less luminous than its primary companion. Together, they complete one orbit around their common center of mass every several thousand years, a slow cosmic waltz witnessed across the galaxy.
The third member of this system, Alnitak c, orbits much farther out, at a distance of roughly 1,000 astronomical units. An astronomical unit, abbreviated AU, is the average distance between Earth and the Sun, about 150 million kilometers. At 1,000 AU, Alnitak c sits at a distance equivalent to about 25 times the separation between our Sun and Neptune, far in the cold outer reaches of the system. Alnitak resides in a region of space rich with gas and dust. Just south of the star, visible through telescopes, lies the Flame Nebula, a glowing cloud of hydrogen gas illuminated by the intense ultraviolet radiation from Alnitak. This nebula appears reddish in photographs, a sign that hydrogen atoms are absorbing energy from the star and re-emitting it as visible light. Beyond the Flame Nebula, though much farther away, sits the famous Horsehead Nebula. This dark silhouette against a brighter background has become one of astronomy's most iconic images. The Horsehead is a dense cloud of dust and gas, opaque to visible light, standing out against the glowing hydrogen of the emission nebula behind it. Alnitak's radiation contributes to illuminating the region, helping create the contrast that makes the Horsehead visible. Now let's turn our attention to the middle star, Alnilam. Its name means string of pearls in Arabic, perhaps referring to the way it sits centered among the belt stars. Alnilam is the farthest of the three from Earth, at a distance of approximately 1,340 light-years. Alnilam is also a blue supergiant, and it's the most luminous of the belt stars. Its mass is estimated at around 40 times that of our Sun, and its diameter spans roughly 75 times the Sun's width. If placed at the center of our solar system, Alnilam would engulf Mercury, Venus, Earth, and Mars, extending almost to the asteroid belt. The star's luminosity reaches staggering levels. Alnilam radiates energy at a rate approximately 400,000 times greater than our Sun. Every second, it pours this enormous quantity of light and heat into surrounding space.
Despite its greater distance compared to Alnitak, Alnilam appears nearly as bright in our sky because of its exceptional luminosity. Alnilam rotates rapidly for a star of its size. Measurements suggest it spins at a speed of around 70 kilometers per second at its equator. This rotation causes the star to bulge slightly at its equator, taking on an oblate shape rather than a perfect sphere. The rapid rotation also drives strong stellar winds, streams of charged particles flowing outward from the star's surface into space. These stellar winds are powerful enough to shape the environment around Alnilam. Gas and dust in the vicinity are pushed outward, creating a region relatively clear of material immediately around the star. Farther out, this ejected material collides with surrounding interstellar gas, creating shock waves and regions of heated, glowing plasma. Alnilam sits in a part of space containing many young stars and active star-forming regions. The Orion molecular cloud complex, one of the most active areas of star formation in our region of the galaxy, surrounds the entire constellation. Alnilam and its companion stars in the belt are all part of the larger Orion OB1 association, a loose group of young, massive stars born from the same giant molecular cloud millions of years ago. Finally, let's consider Mintaka, the westernmost star of the belt, the one that rises first as Orion climbs above the horizon. The name Mintaka comes from Arabic and means the belt. It sits at a distance of roughly 900 light-years from Earth. Like Alnitak, Mintaka is a multiple star system. The primary component, Mintaka A, is actually a close binary system where two massive stars orbit each other every 5.5 days. These two stars are so close together that their outer layers are distorted by mutual gravitational attraction, pulling each star into an elongated, egg-like shape. Mintaka A consists of a bright blue giant and a slightly less massive companion. Together, they have a combined mass of about 50 times our Sun's mass. The primary star has a surface temperature around 30,000 degrees Celsius, giving it an intensely blue-white appearance. The entire Mintaka A system orbits with yet another star, Mintaka B, at a wider separation. Mintaka B is also a massive blue star, though not quite as luminous as the primary pair. The orbital period between Mintaka A and B is not precisely known, but is estimated to be thousands of years, making detailed observation of their motion difficult within human lifetimes. There are additional fainter companions in the Mintaka system as well, making it at least a quintuple star system overall. These fainter stars are much less massive and luminous than the primary components, but they share the same motion through space, bound by the same gravitational well. Mintaka holds a special distinction among the belt stars. It sits almost exactly on the celestial equator. The celestial equator is an imaginary line projected into space from Earth's equator. Stars near the celestial equator rise due east and set due west, regardless of where you observe them from on Earth. This makes Mintaka particularly useful for navigation and for understanding one's position on the planet. When Mintaka is rising, you can be confident that it's appearing directly in the east. When it sets, it descends directly into the west. This reliable behavior helped travelers and sailors for centuries, offering a dependable reference point in the night sky. All three belt stars share certain characteristics. They are all young, all massive, all blue, and all extremely luminous. They all burn their fuel at prodigious rates, living fast and destined to die young in cosmic terms. They are all surrounded by regions of gas and dust, and they all contribute to the ionization and heating of their local interstellar environments. But despite these similarities, they are not gravitationally bound to each other. They do not orbit a common center of mass. They are not a true physical triple system in space. Instead, they are three separate systems, each at different distances from Earth, each with its own history and future, simply aligned by chance along our line of sight.
This alignment is coincidental, the result of our specific vantage point in the galaxy. If you could travel to another star system and look back toward this region, the belt would not appear as a neat line. The stars would be scattered across the sky, their arrangement unrecognizable. The patterns we see in constellations are products of perspective, not physical reality. Understanding this helps us appreciate how three-dimensional space can appear deceptively simple when projected onto the two-dimensional canvas of the sky. It reminds us that the universe has depth, layers, and structure that aren't immediately obvious to the naked eye. It invites us to think more carefully about what we see and what might lie beyond the surface of appearance. The belt stars are all part of a larger structure in our galaxy. They belong to the Orion Arm, also called the Orion Spur, a minor spiral arm of the Milky Way galaxy. Our Sun also resides in this same spiral arm, situated roughly 26,000 light-years from the galactic center. The Orion Arm is densely populated with young stars, star clusters, and nebulae. It's a region where star formation is ongoing, where gravity is pulling together clouds of gas and dust to ignite new generations of stars. The belt stars are products of this process, born within the last 10 million years from collapsing clouds of hydrogen and helium. These stars formed in what astronomers call an OB association, a loose grouping of massive O-type and B-type stars. O and B are classifications based on temperature and spectral characteristics, with O-type stars being the hottest and most massive, and B-type stars being slightly cooler, but still extremely hot by stellar standards. OB associations are common in spiral arms. They represent regions where massive stars have recently formed and are beginning to disperse from their birth sites. The radiation and stellar winds from these massive stars push away the remaining gas and dust, clearing out cavities in the molecular clouds and eventually halting further star formation in the immediate area. Alnitak, Alnilam, and Mintaka are all members of such an association.
They were likely born from the same giant molecular cloud, though not necessarily at the same moment. Their current positions reflect millions of years of independent motion through space, gradually drifting apart as they orbit the center of the galaxy. Each star moves through space with its own velocity, following its own path determined by the gravitational field of the Milky Way and by random motions inherited from the turbulent gas cloud from which it formed. Over millions of years, these motions accumulate, scattering stars that were born together across larger and larger regions of space. If we could watch the sky and fast forward, compressing millions of years into seconds, we would see the belt stars slowly drift apart, their alignment degrading over time. Eventually, tens of millions of years from now, the belt as we know it will no longer exist. New patterns will emerge as other stars move into view, and future observers, if they exist, will tell different stories about different shapes in the sky. But for now, in this era of human history, Orion's belt remains one of the most stable and recognizable patterns in our heavens. Its 3 stars shine steadily, night after night, season after season, unchanged within the span of human lifetimes. They serve as guideposts, as inspirations, and as subjects of endless curiosity. Let's consider what it means for these stars to be blue supergiants. The color of a star tells us about its surface temperature. Our Sun appears yellow-white because its surface temperature is around 5,700 degrees Celsius. Cooler stars, with surface temperatures below 3,500 degrees, appear red or orange. Hotter stars, with temperatures above 10,000 degrees, appear blue or blue-white. The belt stars have surface temperatures exceeding 20,000 degrees Celsius. At these temperatures, most of the light they emit falls into the blue and ultraviolet portions of the electromagnetic spectrum. In fact, they emit so much ultraviolet light our eyes can't see, that if we could see in the ultraviolet, these stars would appear even brighter and more dominant in the sky.
This intense ultraviolet radiation has important consequences for their surroundings. Ultraviolet photons carry enough energy to ionize hydrogen atoms, stripping electrons away from their nuclei. When these free electrons eventually recombine with hydrogen nuclei, they emit light in specific wavelengths, including a characteristic red wavelength called hydrogen alpha. This process causes the nebulae surrounding the belt stars to glow. The Flame Nebula near Alnitak, for example, appears red in photographs because of hydrogen alpha emission. Similarly, regions around Alnilam and Mintaka are bathed in this radiation, causing nearby gas clouds to light up like cosmic neon signs. The term supergiant refers to the star's size and luminosity class. Supergiants are among the largest stars known. They represent a phase in the life of massive stars, occurring after the star has exhausted the hydrogen in its core and begun fusing heavier elements. When a massive star runs out of hydrogen fuel in its core, it can no longer maintain the outward pressure needed to balance gravity's inward pull. The core contracts and heats up, while the outer layers expand enormously. The star grows to many times its original size, becoming a giant, or in the case of the most massive stars, a supergiant. Blue supergiants are typically stars that are still fusing hydrogen in a shell around a helium core, or that have just begun fusing helium in their cores. They haven't yet expanded to the enormous sizes of red supergiants, which represent a later stage of evolution. Blue supergiants are still relatively compact compared to red supergiants, but they are far larger than main sequence stars of the same temperature. The life cycle of a massive star proceeds quickly. A star like Alnitak, with a mass around 30 times that of the Sun, will spend only a few million years fusing hydrogen in its core. For comparison, our Sun has been fusing hydrogen for about 4.5 billion years and will continue for another 5 billion or so. After exhausting core hydrogen, the massive star contracts and heats up, beginning to fuse helium into carbon and oxygen.
This phase lasts only a few 100,000 years. Then it moves on to fuse carbon, then neon, then oxygen, then silicon, each stage happening faster than the last. The silicon burning phase, the final stage before catastrophic collapse, lasts only a few days. At the end of this rapid sequence, the star's core is primarily iron. Iron cannot be fused into heavier elements in a way that releases energy. Fusing iron actually requires energy input rather than releasing it. So when the core becomes iron, there is no more fuel available, and nothing can stop gravity's final victory. The core collapses in less than a second, falling inward at speeds approaching a significant fraction of the speed of light. When the collapse halts, either because of neutron degeneracy pressure or because a black hole forms, an enormous shock wave rebounds outward, ripping through the star's outer layers and blowing them into space in a supernova explosion. This supernova releases as much energy in a few seconds as our Sun will emit over its entire 10 billion year lifetime. The explosion is so bright that for a brief time, the supernova can outshine an entire galaxy. It leaves behind either a neutron star, an incredibly dense ball of neutrons about 20 kilometers across, or a black hole, a region of spacetime where gravity is so strong that not even light can escape. Each of the belt stars will end its life this way. Alnitak, Alnilam, and Mintaka are all destined for supernova explosions. When these events occur, they will be visible from Earth even in daylight. They will appear as brilliant new stars in the sky, perhaps as bright as the full moon, shining steadily for weeks or months before gradually fading. But these explosions are still millions of years in the future for most of these stars. Right now, they are stable, fusing hydrogen or helium in their cores, radiating energy steadily into space, and moving slowly through their allotted lifespans. From Earth, these stars appear as steady points of light. We don't perceive their enormous sizes, their intense heat, or their violent deaths to come.
We see only their light, photons that have traveled for hundreds or thousands of years across empty space to reach our eyes. When you look at Alnitak tonight, you're seeing light that left the star around the year 1200, roughly the time of the Crusades and the early Gothic cathedrals in Europe. When you look at Alnilam, you're seeing light that left around the year 700, early in the European Middle Ages. And Mintaka's light left around the year 1100, when the Song dynasty flourished in China and the First Crusade was yet to begin. This light has traveled through the vacuum of interstellar space, crossing imaginable distances, passing through regions of gas and dust, threading through the gravitational fields of countless stars, until finally, after centuries of travel, it enters Earth's atmosphere, passes through our sky, and reaches your retina. In that moment, across 800 or 900 or 1300 light years, a connection is made. Information encoded in photons, information about temperature, chemical composition, motion, and energy is delivered to you. You become a receiver of data transmitted by a distant star, a participant in the flow of light and knowledge across cosmic distances. This is what makes stargazing so profound. It's not just seeing distant suns, it's connecting with them across time and space, receiving messages sent long before you were born, reading the story written in wavelengths and intensities of light. The belt stars are part of the constellation Orion, named after a hunter in Greek mythology. The ancient Greeks saw in these stars the outline of a mighty figure, with the belt marking his waist, bright stars at his shoulders and feet, and a sword hanging from his belt. Other cultures saw different figures. Some saw a canoe, others saw a group of dancers, and still others saw the footprint of a giant bird. But regardless of interpretation, these stars have been important to humans for as long as we've looked up. They rise in the evening during winter months in the northern hemisphere and summer months in the southern hemisphere.
They're visible from nearly every inhabited place on Earth, making them among the most universally recognized stars in the sky. The constellation Orion contains several other notable stars beyond the belt.
Betelgeuse, a red supergiant marking Orion's right shoulder, is one of the largest stars visible to the naked eye. If placed at the center of our solar system, its surface might extend beyond Mars's orbit. Betelgeuse is nearing the end of its life and could explode as a supernova at any time, meaning any time in the next 100,000 years or so, which is any time on cosmic timescales, even if it's quite distant on human timescales. Rigel, marking Orion's left foot, is another blue supergiant, even more luminous than the belt stars. It's one of the brightest stars in our sky, appearing nearly as bright as Betelgeuse despite being much farther away. Rigel's immense luminosity makes it visible across enormous distances, a beacon shining through the galaxy. Below the belt, visible to the naked eye under dark skies, lies Orion's sword, a line of fainter stars extending downward. In the middle of the sword sits one of the most spectacular objects in the night sky, the Orion Nebula, also known as M42. The Orion Nebula is a vast cloud of gas and dust, glowing with the light of young stars embedded within it. It's a stellar nursery, a place where stars are being born right now, forming from collapsing clumps of hydrogen and helium. The nebula spans about 24 light-years across and lies at a distance of roughly 1,400 light-years from Earth, making it one of the closest major star-forming regions to our solar system. Through even small telescopes, the Orion Nebula appears as a fuzzy greenish patch of light, distinctly different from the sharp points of stars. Larger telescopes and long-exposure photographs reveal astonishing detail: swirls and eddies of glowing gas, dark lanes of obscuring dust, and the bright central region called the trapezium, where 4 massive young stars illuminate the surrounding nebula with their intense radiation.
The Orion Nebula, the belt stars, and the other bright members of the constellation are all part of the same broader structure, the Orion Molecular Cloud Complex. This is one of the largest and most active star-forming regions within about 1,500 light-years of Earth. It contains enough gas and dust to form thousands of stars like our Sun, and star formation is ongoing throughout the complex. The complex consists of several distinct clouds. The Orion Nebula itself is part of the Orion A cloud. North of Orion A lies the Orion B cloud, home to the Horsehead and Flame Nebulae. These clouds are vast, cold, and dense, composed primarily of molecular hydrogen, along with traces of helium and heavier elements. Within these clouds, gravity slowly pulls material together into denser clumps. When a clump reaches sufficient density, its own gravity overwhelms the outward pressure from gas temperature, and it begins to collapse. As it collapses, it heats up, eventually becoming hot enough at its center to ignite nuclear fusion. A new star is born. This process takes millions of years from start to finish, but it's happening constantly throughout the Orion complex, producing new stars continuously. Some of these stars will be small and cool, red dwarfs that will burn for trillions of years. Others will be massive and hot, blue giants like the belt stars, destined for brief, brilliant lives ending in supernova explosions. The most massive stars, like Alnitak, Alnilam, and Mintaka, also play a crucial role in regulating star formation. Their intense radiation and powerful stellar winds push against surrounding gas clouds, compressing some regions and triggering new rounds of star formation, while dispersing other regions and preventing stars from forming. This feedback process creates a cycle. Massive stars form, they compress nearby gas and trigger more star formation. They live for a few million years, and then they explode as supernovae. The supernova explosions inject enormous amounts of energy into the surrounding gas, heating it, pushing it outward, and enriching it with heavy elements forged in the star's core and during the explosion itself. These heavy elements, carbon, oxygen, nitrogen, silicon, iron, and many others, mix with the hydrogen and helium of the interstellar medium. When new stars form from this enriched material, they incorporate these heavy elements. Planets forming around these stars will also contain these elements, which are essential for chemistry, geology, and ultimately life.
Our own sun is a product of this cycle. It formed from gas enriched by previous generations of stars that lived, died, and returned their material to space. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of these elements were created inside ancient stars and distributed into space by supernova explosions billions of years ago. When you look at Orion's belt, you're seeing the current generation of this ongoing cycle. You're witnessing stars in their youth, burning brightly, shaping their environment, and preparing to eventually contribute their own material back to the cosmos, feeding future generations of stars, planets, and perhaps life. There's something humbling and connecting about this realization. We are made of stardust in a very literal sense. The atoms in our bodies are recycled stellar material, forged in the cores of ancient suns and cast into space by violent explosions. We are the universe's way of knowing itself, collections of star-forged atoms organized into structures capable of consciousness, looking back at the stars from which we came. The belt stars shine at us with light that began its journey centuries ago. That light carries information about those stars' temperatures, compositions, motions, and energy outputs. But it also carries a deeper message, that we are connected to these distant suns, that we share a common origin in the cosmic processes of creation and destruction, and that understanding these stars helps us understand ourselves. Let's think about the distances involved more carefully. When we say Alnitak is 815 light-years away, what does that mean? A light-year is the distance light travels in 1 year. Light moves at approximately 300,000 kilometers per second.
In 1 year, that amounts to about 9.5 trillion kilometers, or roughly 63,000 astronomical units. 815 light-years, then, equals about 7.5 quadrillion kilometers. This is a distance beyond human comprehension in everyday terms. If you could travel at the speed of a commercial jet, about 900 kilometers per hour, it would take you roughly 1 billion years to reach Alnitak. By comparison, the universe is only about 13.8 billion years old. Even traveling at the speed of the Voyager spacecraft, the fastest human-made objects ever to leave our solar system, which move at about 17 kilometers per second relative to the Sun, the journey to Alnitak would take roughly 14.5 million years. No human will ever visit these stars. They are too far away, and the laws of physics as we understand them impose strict limits on how fast anything with mass can travel. Traveling at the speed of light is impossible for objects with mass, and even approaching a significant fraction of light speed requires enormous amounts of energy. But light itself makes this journey routinely, effortlessly, constantly. Photons emitted from Alnitak's surface 815 years ago are arriving at Earth right now. As you read this, new photons are streaming towards us, carrying the latest news about the star's condition, though that news is always centuries out of date by the time we receive it. This time delay introduces a strange perspective to astronomy. We can never see things as they are now. We can only see them as they were in the past, when their light began its journey to us. The further away something is, the further back in time we see it. When we observe galaxies billions of light years away, we're seeing them as they were billions of years ago, when the universe was much younger. We're seeing light that has been traveling towards us for most of the age of the universe, crossing billions of light years of expanding space, before finally reaching our telescopes. This makes astronomy a form of time travel, or at least a form of looking into the past.
Every observation is a historical record, a snapshot of conditions in the universe at the time and place the light was emitted. For the belt stars, the time delays are modest compared to cosmological distances, but they're still significant on human timescales. The Alnitak you see tonight looked that way more than 8 centuries ago. If the star exploded as a supernova yesterday in real time, we wouldn't know about it for another 800 years. This also means that our observations of these stars, compiled over the past few centuries of telescopic astronomy, represent an extraordinarily brief moment in their lives.
We've watched them for perhaps 400 years since Galileo first pointed a telescope at the stars. 400 years of a 10 million year lifespan is 0.004%, less than 0.002%. It's like watching a human life for 1 second and trying to draw conclusions about their entire existence. We're seeing a single frozen frame from a multi-million year movie. Almost nothing has changed in the belt stars since humans first noticed them, and almost nothing will change during the entire span of recorded human history. And yet, we've learned enormous amounts about them. Through careful measurement and analysis, through applying physics and mathematics, through building ever more sophisticated instruments and developing deeper theoretical understanding, we've extracted remarkable information from those ancient photons. We know their temperatures to within a few percent. We know their masses to within a factor of about 2 or 3. We know they're in multiple star systems. We know they're moving through space at specific velocities. We know what elements they contain and in what proportions. We know approximately when they formed and approximately when they'll die. This knowledge comes from spectroscopy, the analysis of how stars absorb and emit light at different wavelengths. When light from a star passes through a prism or diffraction grating, it spreads out into a spectrum, a rainbow of colors from red through violet. But this spectrum isn't smooth.
It contains dark lines at specific wavelengths, places where certain colors are missing. These dark lines are absorption lines, created when elements in the star's outer atmosphere absorb photons of specific energies, corresponding to transitions between electron energy levels in atoms. Each element produces a unique pattern of absorption lines, like a fingerprint. Hydrogen produces one set of lines, helium another, iron another, and so on. By measuring which lines are present and how strong they are, astronomers can determine which elements exist in the star and in what relative proportions. The widths and shapes of these lines reveal additional information. The width of a line can indicate temperature, pressure, and turbulence in the star's atmosphere. Shifts in the wavelengths of lines reveal motion toward or away from us due to the Doppler effect. If a star is moving toward us, its light is blue shifted. All the wavelengths are compressed to slightly shorter values, shifting towards the blue end of the spectrum. If it's moving away, its light is red shifted, with wavelengths stretched to longer values. The amount of shift tells us the radial velocity, how fast the star is moving along our line of sight. For the belt stars, measurements show they're all moving away from us at various speeds, typically a few kilometers per second. This motion is part of the overall pattern of motion in our galaxy, as stars orbit the galactic center and also have random velocities in various directions. By measuring these velocities for many stars and combining that information with measurements of their positions in the sky and how those positions change over time, astronomers can reconstruct the three-dimensional positions and motions of stars in our local region of the galaxy. This has confirmed that the belt stars are not physically associated, that they're at different distances and moving in different directions, simply aligned by chance. Another technique called interferometry combines light from multiple telescopes to achieve the resolution of a much larger telescope.
This has allowed astronomers to measure the sizes of some bright stars directly, including Alnitak and Mintaka. By measuring the angular size, how large the star appears on the sky, and knowing its distance, the physical diameter can be calculated. For stars in multiple systems, like Alnitak and Mintaka, orbital motion provides additional information. By watching how the stars move around each other over time, astronomers can apply Kepler's laws of orbital motion to calculate the masses of the stars. This is one of the few direct ways to measure stellar masses, and it provides crucial tests of stellar models. Variability in light output also reveals information. Some stars vary in brightness due to pulsations, expansion and contraction driven by imbalances between gravity and pressure. Others vary because they're eclipsing binaries, where two stars orbit each other and periodically block each other's light from our perspective. Mintaka is an eclipsing binary,
Every 5.73 days, the two stars in the Mintaka A system pass in front of each other as seen from Earth, causing the total brightness to dip slightly. By measuring these dips in detail, their depth, duration, and shape, astronomers can determine the sizes, temperatures, and orbital parameters of the two stars. All of this information, gathered patiently over decades and centuries, builds a detailed picture of what these stars are, how they work, and what their futures hold. It transforms 3 points of light into fully realized astronomical objects, understood in their complexity and placed in context within the broader story of stellar evolution and galactic structure. Yet despite all this knowledge, there remains much we don't know. The exact masses of some belt stars are still uncertain. The details of their internal structure, how energy is transported from core to surface, how convection and radiation interact, are still subjects of ongoing research. The precise timing and mechanism of their eventual supernova explosions can't be predicted with certainty.
We know they'll explode. We know roughly when, within a few million years, but we can't say whether it will be 1 million years, or 5 million years, or 10 million years from now. We don't know what will trigger the final collapse. We don't know exactly what the explosions will look like, or how much material they'll eject, or whether they'll leave behind neutron stars or black holes. These uncertainties don't reflect failures of science, but rather the intrinsic challenges of studying objects so far away, so different from anything we can experiment with directly, and evolving on timescales so slow compared to human lives that we can never watch them change. Science proceeds by building models, testing predictions, refining understanding, and accepting uncertainty where it exists. The picture we have of the belt stars is incomplete, but growing more detailed with time. Each new observation, each new instrument, each new theoretical insight adds another piece to the puzzle. And the puzzle itself is beautiful. Even incomplete, even with uncertainties remaining, the story of Orion's belt is rich with meaning and wonder. 3 stars, hundreds of light years apart, each a sun far more mighty than our own, each shining with the fierce light of youth, each destined for a spectacular end, all lined up by chance in our sky, guiding travelers and inspiring stories for as long as humans have looked up at night. This is the story told by science, a story grounded in measurement and observation, in physics and chemistry, in mathematics and logic, but no less wondrous for being true. Perhaps it's more wondrous because it's real, because it connects us to actual places and processes in the universe, because it reminds us that we live in a cosmos stranger and more magnificent than any mythology could imagine. So when you see those 3 stars tonight, arranged in their perfect line, remember what they truly are. Remember their heat, their size, their age, their fate. Remember the distances they span, the light years of empty space between them. Remember the time delay, the centuries-old light reaching your eyes.
Remember that you're seeing not just 3 stars, but 3 entire stellar systems, each complex, each unique, each with its own story. And remember, too, that we are part of this story. We are made from the same materials, forged in the same processes. We are, quite literally, star children, looking back at our origins, seeking to understand the mechanisms that created us, finding meaning and beauty in the contemplation of cosmic immensity and our tiny but significant place within it. The nebulae and the birth of stars. The space around Orion's belt is not empty. Between the stars, filling the vast distances, lies material, gas and dust, thin beyond imagination by earthly standards, yet present everywhere, forming clouds and currents, dark lanes and glowing regions, invisible structures revealed only through careful observation. This interstellar medium, as astronomers call it, is the raw material from which stars are born and to which they return their substance when they die.
It is ancient and ever-renewing, a cosmic ocean through which stars swim, from which they emerge, and into which they eventually dissolve. Around the belt stars, this medium takes visible form as nebulae, clouds of gas illuminated by stellar radiation or silhouetted against brighter backgrounds. These nebulae are not merely beautiful objects for telescopes to photograph. They are active participants in the ongoing story of creation and destruction that defines our galaxy. Let us begin with the Flame Nebula, designated NGC 2024 in astronomical catalogs. This nebula sits just east of Alnitak, so close in the sky that the star's brilliant light often overwhelms the nebula's fainter glow when viewed through small telescopes. But long-exposure photographs reveal its structure clearly, a complex region of glowing hydrogen gas threaded with dark lanes of obscuring dust. The Flame Nebula appears to glow with reddish light, characteristic of hydrogen emission. This glow comes from a process called photoionization. Ultraviolet photons from Alnitak strike hydrogen atoms in the nebula, providing enough energy to knock electrons free from their nuclei.
The nebula becomes a plasma, a hot gas of free electrons and ions. When these electrons eventually recombine with hydrogen nuclei, they cascade down through various energy levels, emitting photons at specific wavelengths. The brightest of these emissions, the one that gives the nebula its red appearance, occurs at a wavelength of 656.3 nanometers, called hydrogen alpha or H-alpha. This wavelength falls in the red part of the visible spectrum, which is why emission nebulae typically appear red in photographs. Our eyes, less sensitive than cameras and adapted for daylight vision, usually perceive these nebulae as grayish or greenish when viewing them through telescopes directly, but long exposures on camera sensors or photographic film capture the true color. The Flame Nebula extends roughly 2.5 light-years across. Within this cloud, the density of gas is higher than in typical interstellar space, but still incredibly tenuous by earthly standards. In the densest parts of the nebula, there might be 10,000 atoms per cubic centimeter. For comparison, air at sea level on Earth contains about 10 to the power 19 molecules per cubic centimeter, 1,000,000 trillion times denser. Yet even this tenuous material is thick enough to block light from stars behind it. The dark lanes cutting through the Flame Nebula are composed of dust grains, tiny particles of carbon, silicon, and other elements, each perhaps 1/10 of a micrometer across. These grains are effective at scattering and absorbing starlight, creating regions that appear dark against the glowing hydrogen background. Behind these dark lanes, star formation is occurring. Observations in infrared wavelengths, which can penetrate dust that blocks visible light, reveal clusters of young stars embedded in the Flame Nebula. These stars are still in early stages of development, some still surrounded by disks of gas and dust from which planets might eventually form. The process of star formation begins when a region of a molecular cloud becomes gravitationally unstable.
This can happen for various reasons: the compression caused by a nearby supernova explosion, the collision of two clouds, the gravitational influence of the spiral density wave in the galactic disk, or simply random fluctuations in density that happen to reach a critical threshold. Once a region begins to collapse, gravity pulls material inward toward the center. As material falls inward, it heats up due to compression, converting gravitational potential energy into thermal energy. The collapsing cloud fragments into smaller clumps, each of which may form an individual star or a multiple star system. At the center of each collapsing clump, a protostar forms. This is not yet a true star. Nuclear fusion has not begun. It shines only with the heat generated by gravitational contraction, glowing in infrared wavelengths. Material continues to fall onto the protostar, increasing its mass and temperature. This accretion process is not smooth. Material falls in through a swirling disk, an accretion disk, that forms around the protostar due to conservation of angular momentum. As material spirals inward through this disk, friction heats it to high temperatures, causing it to radiate energy.
Young protostars are often surrounded by bright, hot accretion disks visible in infrared observations. The protostar also launches powerful jets perpendicular to the disk, streams of material ejected at high speeds along the rotation axis. These jets plow into surrounding gas, creating shockwaves and glowing regions called Herbig-Haro objects. The mechanism that drives these jets is not fully understood, but appears to involve magnetic fields that channel material away from the protostar. As the protostar continues to accumulate mass, its core temperature and pressure rise. When the core temperature reaches about 10 million degrees Celsius, hydrogen nuclei begin to overcome their mutual electrical repulsion and fuse together, forming helium and releasing energy in the process. This is nuclear fusion, the power source that will sustain the star for the rest of its life. When fusion begins, the protostar becomes a true star.
The energy produced by fusion creates an outward pressure that balances the inward pull of gravity, and the star settles into a stable configuration. It joins the main sequence, the long stable phase during which it will fuse hydrogen in its core for millions or billions of years, depending on its mass. For massive stars like those being born in the Flame Nebula, this entire process from initial collapse to main sequence star takes only about 100,000 years. For smaller stars like our Sun, it takes about 50 million years. The more massive the star, the faster it forms, and the faster it will eventually exhaust its fuel. The young stars in the Flame Nebula are probably less than a few million years old. They are clearing away the gas and dust in their vicinity through radiation pressure and stellar winds, creating bubbles and cavities in the cloud. Eventually, they will disperse the entire nebula, leaving behind a young open cluster of stars that will gradually drift apart over hundreds of millions of years. This pattern repeats throughout star-forming regions. The Orion Nebula, visible below the belt, is another such region, perhaps the most intensely studied stellar nursery in the entire sky. Designated M42 or NGC 1976, it lies at a distance of approximately 1,440 light-years from Earth, making it one of the closest major star-forming regions to our solar system. The Orion Nebula is enormous, spanning roughly 24 light-years across. Its total mass is estimated at about 2,000 times the mass of our Sun, enough raw material to form thousands of stars. Much of this mass is concentrated in denser clumps within the nebula, regions where star formation is actively occurring. At the heart of the Orion Nebula lies the trapezium, a tight cluster of 4 bright stars visible through even small telescopes. These stars, designated Theta 1 Orionis A, B, C, and D, are young and massive, probably less than 1 million years old. The brightest, Theta 1 Orionis C, is a blue giant with a mass about 40 times that of the Sun and a luminosity roughly 300,000 times greater.
These 4 stars provide most of the ultraviolet radiation that illuminates the Orion Nebula, causing it to glow with the characteristic red light of hydrogen emission. But infrared observations reveal that the trapezium is actually a much larger cluster, containing hundreds of additional stars, too faint or too obscured by dust to see in visible light. Many of these young stars are still surrounded by protoplanetary disks, flattened clouds of gas and dust rotating around the star. These disks are planetary systems in formation, regions where dust grains are colliding and sticking together, gradually building up into larger objects, pebbles, boulders, asteroids, and eventually planets. The Hubble Space Telescope has captured images of these protoplanetary disks in the Orion Nebula, showing them silhouetted against the bright nebular background. They appear as dark tadpole-shaped structures, with the forming star at the head and a tail of material streaming away, blown by radiation from the nearby massive stars. These disks are evidence that planet formation is a natural and common outcome of star formation. Our own solar system formed from such a disk 4.5 billion years ago, around a newly formed star we now call the Sun.
The planets, moons, asteroids, and comets in our solar system are the leftover pieces and assembled products of that ancient disk. Studying protoplanetary disks in regions like the Orion Nebula allows astronomers to observe the planet-forming process in action. We can see how disks evolve over time, how material clumps together, how gaps open up as forming planets sweep clear their orbital paths. We can measure the sizes, masses, and compositions of these disks, testing models of planet formation and refining our understanding of how planetary systems like our own come to be. The Orion Nebula is only one part of a much larger structure, the Orion Molecular Cloud Complex. This complex extends across much of the Orion constellation, encompassing several distinct clouds of molecular gas, each with its own star-forming regions, young star clusters, and illuminated nebulae. The two main components are called Orion A and Orion B.
Orion A contains the Orion Nebula and stretches southward from the belt. Orion B lies north of the belt and contains the Horsehead and Flame Nebulae. Together, these clouds contain hundreds of thousands of solar masses of molecular hydrogen, the fundamental building block from which stars form. Molecular hydrogen, H2, is a molecule consisting of two hydrogen atoms bonded together. It is the most common molecule in the universe and the primary constituent of molecular clouds. At the low temperatures typical of molecular clouds, around 10 to 50 degrees above absolute zero, hydrogen exists primarily in this molecular form rather than as individual atoms. Molecular hydrogen itself is difficult to observe directly because it doesn't emit much light at these low temperatures. Instead, astronomers trace molecular hydrogen by observing other molecules that are present in trace amounts, particularly carbon monoxide, CO. Carbon monoxide emits radio waves at specific frequencies when it rotates, and these emissions can be detected by radio telescopes, even when the cloud is too cold and dark to see invisible light. By mapping the distribution and motion of carbon monoxide throughout a molecular cloud, astronomers can infer the distribution of molecular hydrogen and study the structure and dynamics of the cloud. These observations reveal that molecular clouds are not uniform, but rather have complex filamentary structures with denser cores connected by more tenuous filaments. Star formation occurs primarily in the densest cores, where gravity can overcome the internal pressure of the gas and cause collapse. The filaments appear to channel material into these cores, feeding the star-forming process. The entire cloud is turbulent, with gas flowing in complex patterns driven by gravity, stellar winds, expanding bubbles blown by massive stars, and shocks from supernova explosions. This turbulence both promotes and inhibits star formation. In some regions, compression from turbulent flows triggers collapse and star formation. In other regions, turbulence provides enough random motion to resist gravitational collapse, keeping the gas dispersed.
The interplay between gravity, pressure, turbulence, magnetic fields, and radiation creates a rich and complex environment where star formation occurs at a rate determined by the balance of these competing processes. Magnetic fields play an important but still poorly understood role in this process. Molecular clouds are threaded with magnetic fields, generated by complex processes involving rotating charged particles and turbulent flows. These fields exert forces on the ionized component of the gas, which is coupled to the neutral gas through collisions. Magnetic fields can slow down or prevent the collapse of gas clouds by providing additional pressure support. Material must slip across field lines to fall toward the center of a collapsing core, a process that takes time and introduces delays. Magnetic fields can also channel material along field lines, affecting the geometry of collapse and the formation of jets and outflows from young stars. Observations of magnetic fields in molecular clouds are challenging, but have become more feasible in recent years through techniques like measuring the polarization of light from background stars. Dust grains in the cloud align themselves with the local magnetic field, and this alignment affects the polarization of starlight passing through the cloud.
By measuring how polarization varies across a cloud, astronomers can map the magnetic field structure and study its influence on star formation. Another important component of the interstellar medium is dust. Interstellar dust consists of tiny solid particles, typically about 1/10 of a micrometer in diameter, smaller than the wavelength of visible light. These grains are composed primarily of carbon, in the form of graphite or complex organic molecules, and silicates, compounds of silicon and oxygen. Despite being individually tiny, dust grains are critically important for many processes in the interstellar medium. They scatter and absorb starlight, creating dark nebulae, and reddening the light from stars behind them. They also serve as surfaces where chemical reactions can occur, including the formation of molecular hydrogen itself.
In the cold conditions of molecular clouds, atoms and molecules that collide with dust grains can stick to their surfaces. On these surfaces, atoms can meet and bond, forming molecules that would be difficult to form in the gas phase. Molecular hydrogen forms primarily on dust grain surfaces, as do many other molecules detected in molecular clouds, including water, methanol, and ammonia. Dust grains also play a crucial role in planet formation. In protoplanetary disks, dust grains collide and stick together through a combination of electrostatic forces, surface adhesion, and gravity. This process, called accretion, gradually builds up larger and larger objects. Small grains become pebbles, pebbles become boulders, boulders become kilometer-sized planetesimals, and planetesimals eventually collide and merge to form planets. Understanding dust is therefore essential for understanding both star formation and planet formation. Yet dust remains challenging to study. Its composition, size distribution, and behavior vary from one environment to another. In the dense cores of molecular clouds, dust grains may grow by accretion of ice mantles, layers of frozen water, carbon dioxide, and other molecules. In regions near hot stars, dust can be destroyed by intense radiation or high temperatures. The Horsehead Nebula, one of the most iconic astronomical images, is a dark nebula, a cloud of dust so dense that it blocks light from the glowing hydrogen behind it. Designated Barnard 33, it is part of the Orion B cloud and sits just south of Alnitak. The nebula's distinctive shape, resembling the head and neck of a horse, is visible in photographs as a dark silhouette against the bright emission nebula IC 434. The Horsehead is a small part of a much larger dark cloud. The visible horse's head is a protruding pillar of dense gas and dust, sculpted by the radiation from nearby stars. Ultraviolet light from Sigma Orionis, a multiple star system just off the left edge of most Horsehead images, and from Alnitak, illuminates IC 434, causing it to glow red with hydrogen emission.
This radiation also erodes the edges of the dark cloud, gradually eating away at it and causing the densest parts to stand out in relief. The Horsehead itself is such a dense knot, resistant enough to erosion, that it remains visible while surrounding material is slowly dispersed. Over millions of years, even the Horsehead will be eroded away, leaving no trace. Within the Horsehead, star formation may be occurring. Infrared observations have detected a young star near the top of the nebula, still embedded in the dense gas from which it formed. This star is probably very young, perhaps only a few 100,000 years old, and still surrounded by material left over from its formation. The Horsehead Nebula lies at approximately the same distance as the belt stars, around 1,200 to 1,500 light-years from Earth. It is part of the same star-forming complex, the same larger structure of gas and clouds from which Alnitak, Alnilam, and Mintaka emerged millions of years ago. This raises an interesting point. The belt stars, the Orion Nebula, the Horsehead, the Flame, all of these objects are related through a shared history. They are all products of the same giant molecular cloud, or at least clouds that are connected and part of the same large-scale structure. Tens of millions of years ago, the region now occupied by Orion contained a much larger and more massive molecular cloud. This cloud began to collapse and fragment, forming multiple generations of stars. The oldest stars have already dispersed, drifting away from their birthplace and spreading throughout this part of the galaxy. Younger stars, like the belt stars, formed more recently and have not yet had time to disperse far from where they were born. The youngest stars, like those in the Orion Nebula and the Flame Nebula, are still embedded in the gas from which they formed. They are in the process of dispersing their birth clouds, blowing bubbles and clearing cavities through radiation and stellar winds. In a few million more years, they too will have cleared away the surrounding gas, and new star formation in this region will cease until fresh gas flows in from elsewhere in the galaxy.
This is the pattern of star formation in spiral galaxies like our Milky Way. Molecular clouds form, stars are born. Massive stars live and die quickly. Their supernovae compress surrounding gas and trigger new rounds of star formation. And over tens of millions of years, the clouds are gradually dispersed, recycled, and reformed elsewhere. The spiral arms of galaxies, visible in photographs as bright, winding lanes, are not permanent structures, but rather density waves, regions where gas and dust are compressed and star formation is enhanced. As gas flows through a spiral arm, it is compressed, triggering collapse and star formation. The newly formed massive stars illuminate the arm with their brilliant blue light, creating the characteristic bright arms seen in spiral galaxy images. But the stars don't remain in the spiral arm. They continue to orbit the galactic center and gradually drift out of the arm as they age. Meanwhile, new gas flows into the arm and the cycle continues. The spiral arm pattern persists, even though the material composing it is constantly changing, much like a traffic jam persists, even though the individual cars within it are constantly moving through and being replaced by new cars. Orion sits in a minor spiral arm called the Orion Spur, or Orion Arm, positioned between two major arms of the Milky Way. Our Sun also resides in this arm, which is why we see so much active star formation when we look toward Orion. We're looking along the arm, seeing through layers of gas, dust, and young stars that share our location in the galactic disk. The Orion arm is not a major spiral arm, but rather a smaller structure, sometimes described as a spur or a bridge between the larger Sagittarius and Perseus arms. It extends several thousand light-years and contains numerous molecular clouds, star formation regions, and young star clusters. Among these are not only the Orion complex, but also other well-known regions like the Taurus molecular cloud and the Perseus molecular cloud. Each of these regions contains hundreds to thousands of young stars in various stages of formation and evolution, along with the gas and dust from which future stars will form.
The distribution of molecular clouds and star-forming regions in the Milky Way is not uniform. Star formation is concentrated in spiral arms, particularly in the dense, cold molecular clouds. Between the arms, in the inter-arm regions, star formation is much less common, though some stars do form in smaller, isolated clouds. The rate of star formation in the Milky Way is estimated at about 1 to 3 solar masses per year. This means that every year, enough stars are born in our galaxy to total the mass of 1 to 3 suns like our own. This may sound like a lot, but given that the Milky Way contains several hundred billion stars already, this rate means the galaxy is converting only a tiny fraction of its gas into stars each year. Most of the galaxy's gas remains in the form of atomic or molecular hydrogen in the interstellar medium. Only in the densest, coldest clouds does gas collapse to form stars, and even then, only a small fraction of the cloud's mass ends up in stars. Much of the gas is blown away by stellar winds and supernova explosions before it can form stars, recycled back into the diffuse interstellar medium to perhaps participate in future star-forming episodes. This inefficiency of star formation is actually crucial for maintaining the galaxy over billions of years. If star formation were too efficient, all the galaxy's gas would be converted into stars within a few billion years, and no new stars would form. The galaxy would gradually fade as its stars aged and died without replacement. But because star formation is inefficient and because dying stars return much of their mass to the interstellar medium, the galaxy maintains a supply of gas for ongoing star formation. The cycle of birth, life, death, and recycling continues, allowing galaxies like the Milky Way to remain active and star-forming for billions of years. The Orion region provides a local, relatively nearby example of this cycle in action. We can observe star formation happening in real time, or at least on timescales short enough that meaningful changes occur within human lifetimes or within the span of a few decades of observations.
Astronomers have watched young stars vary in brightness as material falls onto them from surrounding disks. They've observed jets and outflows change shape and intensity over years. They've seen protostars emerge from cocoons of dust as they heat up and disperse their surroundings. These observations provide crucial tests of star formation theories and help refine our understanding of the physical processes involved. One particularly interesting class of young stars is the T Tauri stars, named after the prototype star T Tauri located in the Taurus molecular cloud. These are pre-main sequence stars, stars that have formed but have not yet settled into stable hydrogen burning. They are typically less than 10 million years old and are still contracting toward their final main sequence configuration. T Tauri stars vary irregularly in brightness, sometimes dramatically, over timescales of days to years. This variability is caused by several factors: material falling onto the star from an accretion disk, hotspots where infalling material impacts the stellar surface, cool spots analogous to sunspots on the sun, and obscuration by clumps of dust in the surrounding disk. Many T Tauri stars also exhibit powerful winds and jets. These outflows can carry away significant amounts of mass and angular momentum, helping the star lose the excess rotation it inherited from the rotating cloud from which it formed. Without this angular momentum loss, the star would rotate so fast that centrifugal force would prevent further contraction. Hundreds of T Tauri stars have been identified in the Orion region, providing a rich sample for studying the early stages of stellar evolution. These stars are embedded in and surrounded by the nebulosity of the molecular cloud, creating a complex and beautiful environment, visible in both optical and infrared wavelengths. Infrared observations are particularly valuable for studying young stars, because infrared light can penetrate the dust that often obscures these objects in visible light.
Infrared telescopes like the Spitzer Space Telescope and the James Webb Space Telescope have revealed the detailed structures of protoplanetary disks, the presence of young stars still hidden in dense cores, and the distribution of complex organic molecules in star-forming regions. These observations have shown that the planet-forming process begins early, even while the star is still accreting material. Dust grains in the disk begin to grow and settle toward the disk's midplane within the first 100,000 years. By 1 million years, kilometer-sized planetesimals may have formed in some disks. By 10 million years, planets may have assembled, and the disk's gas may have largely dispersed, leaving behind a debris disk of leftover planetesimals. Our own solar system went through these stages 4.5 billion years ago. The planets formed within about 50 to 100 million years, and the gas disk dispersed, leaving the planets orbiting in a stable configuration that has persisted with only minor changes ever since. The heavy bombardment period, when leftover planetesimals rained down on the newly formed planets, lasted a few 100 million years and ended about 3.8 billion years ago. Earth's surface was heavily cratered during this period, though plate tectonics and erosion have since erased most of these ancient impact scars. By comparison, the Moon's surface still bears the scars of this bombardment. The dark maria, the large, smooth areas visible to the naked eye, are ancient impact basins filled with solidified lava. They date to the late heavy bombardment period and have remained largely unchanged since then because the Moon has no atmosphere, no water, and no plate tectonics to modify its surface. Looking at the Moon, we're seeing a preserved record of what the early solar system was like, a reminder of the violent and chaotic conditions during planet formation.
The Orion Nebula and other star-forming regions allow us to see similar processes happening elsewhere right now, building planetary systems around distant stars, creating the potential for new worlds where life might someday arise.
This connection between star formation and the possibility of life is profound. Every star with planets, every planet with the right conditions, represents a potential site where complex chemistry could lead to biology, where life could emerge and evolve. We don't know how common life is in the universe. We have only one example, life on Earth, and we don't fully understand how it originated or how likely such an origin is. But we do know that the basic ingredients are common. Organic molecules, complex carbon-containing compounds, have been detected in molecular clouds, in comets, in meteorites, and in protoplanetary disks. Water is also abundant. It's found as ice on comets and asteroids, as ice mantles on dust grains in molecular clouds, and as vapor in the atmospheres of distant planets. The elements necessary for life, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, are all produced in stars and distributed into space through stellar winds and supernova explosions. The conditions necessary for life, liquid water, a stable energy source, a protective atmosphere, are likely present on some planets around other stars. Astronomers have discovered thousands of exoplanets, planets orbiting stars other than the Sun, and some of these planets are similar in size to Earth and orbit at distances where liquid water could exist on their surfaces. Whether any of these planets actually harbor life is unknown. We haven't yet developed the technology to detect life on distant planets directly. But future telescopes, both in space and on the ground, may be able to analyze the atmospheres of Earth-like exoplanets, searching for gases like oxygen and methane that could indicate biological activity. If life exists elsewhere, it may have originated in environments similar to the ones we observe in star-forming regions. Newly formed planets, enriched with organic molecules from their protoplanetary disks, warmed by their parent stars, could provide settings where chemistry gradually transitions to biology. This possibility makes the study of star formation and planet formation deeply relevant, not just to astronomy, but to biology and philosophy as well.
Understanding how stars and planets form is part of understanding how life itself becomes possible, how the universe creates conditions where complexity, order, and eventually awareness can emerge from the simple raw materials of hydrogen and helium. The belt stars, massive and short-lived, will not host life themselves. They burn too hot, live too briefly, and will end their lives in supernova explosions long before biological evolution could proceed very far on any planets they might have. But the smaller stars forming in the same regions, stars more like our Sun, could potentially host life. These stars will live for billions of years, providing stable environments where planets can evolve and life can emerge, adapt, and diversify. Somewhere in the Orion Nebula, among the thousands of young stars visible in infrared images, there may be a star that will one day host a living world. Its planets are forming now, from the same disk of gas and dust that surrounds the star. Over the next few million years, these planets will grow, atmospheres will develop, and conditions will stabilize. Billions of years from now, when that star has settled into its main sequence lifetime, when its planets have cooled and solidified, liquid water might condense on a rocky surface. Organic molecules delivered by comets or synthesized in the atmosphere might accumulate in those waters. Chemistry might become biochemistry. Life might begin. This is speculation, of course. We have no direct evidence that this will happen, but the processes that led to life on Earth, star formation, planet formation, the delivery of water and organic molecules, the establishment of stable conditions, are universal processes happening throughout the galaxy, throughout the universe. If life arose on Earth from these processes, it seems plausible that it could arise elsewhere as well. The universe is vast, ancient,
and filled with stars and planets. Even if life is rare, the sheer number of opportunities suggests that we are unlikely to be alone. This perspective, emerging from the study of star-forming regions like Orion, transforms our understanding of our place in the cosmos.
We are not separate from the universe, observers standing outside looking in. We are participants, products of the same processes we study, made of the same materials, governed by the same laws. When we look at Orion's belt, we're looking at a place where the raw materials of future worlds are being assembled. We're seeing stars being born that might one day be the suns for distant civilizations. We're witnessing the cosmic cycle that created us, that created Earth, that created the conditions for life to arise here and perhaps elsewhere. This knowledge doesn't diminish wonder, it enhances it. The universe revealed by science is more intricate, more beautiful, and more awe-inspiring than anything imagined by ancient mythologies. The 3 stars of the belt are not just points of light, but gateways to understanding the processes that shape galaxies, form stars, build planets, and create the potential for life. And all of this unfolds slowly, gradually, following natural laws that we've learned to understand through observation, experiment, and mathematical reasoning. There's no rush, no urgency. The universe operates on its own timescale, indifferent to human impatience, creating beauty and complexity through patience and time. Star formation in Orion will continue for millions of years to come. New stars will emerge from the molecular clouds, illuminating new nebulae, creating new patterns in the sky. Eventually, the clouds will disperse, star formation will cease in this region, and the young stars will drift apart, spreading throughout the galaxy, carrying with them the atoms and molecules that once comprised the Orion molecular cloud complex. Some of those atoms, billions of years from now, might find themselves on planets orbiting those stars. Some might be incorporated into living organisms, if life arises. Some might become part of thinking beings who look up at their own night sky and wonder about the universe, just as we do. This is the cycle, the pattern, the story told by the stars. It's a story of creation and destruction, of order emerging from chaos, of complexity arising from simplicity. It's a story that includes us, that explains where we came from and hints at where we might be going. The belt stars, the nebulae, the forming planets, all of these are chapters in this larger story. By studying them, we're learning to read the story, to understand its grammar and syntax, to appreciate its depth and meaning. And there's something deeply satisfying about this understanding, something that resonates with our need to make sense of existence. We find ourselves in a universe that is knowable, that follows rules, that can be understood through reason and observation. We find that we are not strangers here, but rather natural products of cosmic processes, at home in a universe that created us. This perspective, grounded in science, informed by careful observation, supported by measurement and analysis, offers a foundation for meaning that is both humbling and empowering. We are small, insignificant in spatial extent, brief in temporal duration, localized in one tiny corner of an enormous cosmos. Yet we are significant. We are the universe's way of knowing itself, of reflecting on its own existence, of finding pattern and meaning in its processes. We are, in a very real sense, the universe becoming conscious of itself, looking back at its own history, understanding its own nature. When you gaze at Orion's belt tonight, you're participating in this self-reflection. You're using your eyes, evolved over millions of years of biological evolution, shaped by natural selection, to gather information about the world, to capture photons that have traveled across hundreds of light years of space. You're using your brain, the most complex structure we know of in the universe,
to process that information, to recognize patterns, to generate understanding. And through that understanding, you connect with something larger than yourself. You become part of the story, a conscious participant in the cosmic drama of creation, evolution, and understanding. You become a thread in the vast tapestry of existence, woven together with stars and galaxies, with time and space, with matter and energy, into a unified whole.
This is what science offers us. Not just facts and figures, not just measurements and equations, but a way of seeing ourselves as part of the universe, connected to everything else through shared history and common processes. It offers a sense of belonging, of participation, of meaning grounded in reality rather than wishful thinking. The belt stars shine on, indifferent to our observations, following their own trajectories through space and time. They will continue to shine long after we're gone, unchanged by our existence, unaffected by our thoughts and theories. Yet in observing them, in studying them, in understanding them, we've made them part of human culture, human knowledge, human meaning. We've taken something distant and impersonal and made it ours, not through possession, but through understanding. This is the gift of astronomy, the contribution of science to human life. It extends our reach beyond our immediate surroundings, beyond the limits of our senses, into realms of space and time that dwarf human experience. It allows us to see farther, think deeper, and understand more than would otherwise be possible. And it does all this not through mysticism or revelation, but through patient observation, careful reasoning, and honest assessment of evidence. It builds knowledge incrementally, testing ideas against reality, discarding what doesn't work, refining what does, gradually constructing an ever more accurate picture of how the universe operates. This process is ongoing. We haven't finished understanding the universe. We haven't answered all questions or solved all mysteries. Star formation still holds unknowns. Planet formation has details we don't yet understand. The origins of life remain mysterious. The nature of consciousness is unclear. But we are making progress. Each generation adds to the accumulated knowledge, building on what came before, pushing the boundaries of understanding a little farther. And the direction of progress is clear, toward greater understanding, more detailed knowledge, deeper appreciation of the complexity and beauty of the natural world.
The Orion region, with its bright stars, glowing nebulae, and active star formation, provides a laboratory for this ongoing investigation. It's close enough to study in detail, active enough to show interesting processes, and rich enough in phenomena to keep astronomers busy for generations to come. Every new instrument, every new observation, every new technique reveals something new about this region. We're still discovering young stars in the molecular clouds, still finding protoplanetary disks around those stars, still measuring the properties of the nebulae and the dust and the magnetic fields. And as we learn more about Orion, we learn more about star formation in general, about how the process works throughout the galaxy, throughout the universe. The details we observe here inform our understanding of distant galaxies, of conditions in the early universe, of how the first stars formed after the Big Bang. Science builds connections like this, linking local observations to universal principles, showing how the same physical laws apply everywhere, creating a unified framework for understanding the entire cosmos. This unity is one of the most remarkable discoveries of modern science, that the universe is, fundamentally, a coherent whole, governed by a relatively small number of basic principles that apply everywhere and at all times. Gravity works the same way in Orion as it does on Earth. Nuclear fusion follows the same rules in the belt stars as it does in the Sun. The laws of thermodynamics, the behavior of light, the properties of atoms, all are universal,
allowing us to understand distant objects by studying nearby examples and applying those lessons across cosmic distances. This universality makes astronomy possible. Without it, we couldn't hope to understand stars and galaxies from our remote vantage point on Earth. But because nature is consistent, because the same rules apply everywhere, we can study light from distant objects and extract detailed information about their properties, compositions, and behaviors. The belt stars, though separated from us by hundreds of light years of empty space, are knowable.
We can determine their masses, temperatures, luminosities, and compositions. We can predict their futures and reconstruct their pasts. We can place them in context within the larger story of stellar evolution and galactic structure. And in doing so, we satisfy a deep human need, the need to understand, to make sense of our surroundings, to find order and pattern in what might otherwise seem chaotic and meaningless. The future written in light. Time moves differently for stars than it does for us. A human lifetime, measured in decades, represents only the briefest flicker in the life of a star. Civilizations rise and fall, species evolve and go extinct, continents drift across planetary surfaces, and still the stars burn on, largely unchanged, following trajectories laid out by physics and gravity across millions or billions of years. The belt stars, Alnitak, Alnilam, and Mintaka, are no exception to this cosmic patience. They shine tonight as they shone 1,000 years ago, as they will shine 1,000 years from now. To human observers, they appear eternal, fixed points in a changing world. But they are not eternal. They are temporary structures, burning through their fuel at tremendous rates, racing toward inevitable ends. Let us consider what the future holds for these three blue giants. Let us trace their remaining lives forward through time, following the path laid out by stellar physics, understanding what must eventually occur when massive stars exhaust their nuclear fuel. Alnitak, the easternmost star of the belt, has been burning for approximately 6 million years. Its mass, roughly 33 times that of our Sun, determines the rate at which it consumes its hydrogen fuel. The more massive a star, the hotter its core must be to generate enough pressure to support its weight against gravity's inward pull. Higher temperatures mean faster fusion reactions, which means faster fuel consumption. While our Sun will fuse hydrogen in its core for about 10 billion years total, Alnitak will exhaust its core hydrogen in perhaps 10 million years, 1,000 times faster. It has already lived through more than half of its main sequence lifetime.
Within a few million more years, possibly as few as 3 or 4 million, it will run out of hydrogen in its core. When this happens, the core will begin to contract. As it contracts, it heats up, and this heat ignites hydrogen fusion in a shell around the now inert helium core. The energy from this shell fusion pushes the star's outer layers outward, causing the star to expand. Alnitak will grow larger, though it will also become somewhat cooler at its surface, transitioning perhaps toward a blue or yellow supergiant phase. Eventually, the core will become hot enough, about 100 million degrees Celsius, to begin fusing helium into carbon and oxygen. This helium fusion releases tremendous energy, stabilizing the star temporarily in a new configuration. But helium burns much faster than hydrogen. A star that spent millions of years fusing hydrogen might fuse its core helium in only a few 100,000 years. After helium is exhausted, the pattern repeats. The core contracts, heats up, and if the star is massive enough, which Alnitak certainly is, begins fusing carbon. Carbon fusion produces neon, sodium, and magnesium. Then neon fusion produces oxygen and magnesium. Then oxygen fusion produces silicon and sulfur. Finally, silicon fusion produces iron,
Each stage proceeds faster than the one before. Carbon fusion might last a few thousand years, neon fusion a few years, oxygen fusion a few months, silicon fusion just a few days. This acceleration happens because each successive fusion reaction releases less energy per unit mass fused. To maintain the outward pressure needed to support the star's weight, fusion must proceed at ever-increasing rates, burning through fuel ever more quickly, racing toward the moment when no more energy can be extracted. Iron is the end of the line. Iron nuclei are the most tightly bound of all atomic nuclei. Fusing iron into heavier elements doesn't release energy, it requires energy input. When the core becomes primarily iron, there is no more fuel available. The core can no longer generate the energy needed to support the star against gravity. At this point, catastrophe is inevitable. The core collapses.
In less than a second, a region the size of Earth compresses down to a sphere about 20 kilometers across. The density becomes so extreme that atomic nuclei merge together and electrons are forced to combine with protons, creating neutrons. The core becomes a ball of neutrons, supported against further collapse only by neutron degeneracy pressure, a quantum mechanical effect that prevents neutrons from occupying the same quantum state. When the collapse halts, a shock wave rebounds outward, carrying immense energy. This shock wave blows the star's outer layers into space at speeds of tens of thousands of kilometers per second. The explosion releases as much energy in a few seconds as our sun will emit over its entire 10 billion year lifetime. For weeks, the supernova shines with the luminosity of billions of suns, briefly outshining the entire galaxy in which it occurs. This is the fate awaiting Alnitak. Sometime in the next few million years, probably sooner rather than later on cosmic timescales, it will explode as a Type II supernova. The explosion will be visible from Earth even in daylight, appearing as a brilliant new star, perhaps as bright as the half moon or even the full moon, depending on the details of the explosion. The supernova will remain visible for months, gradually fading as the ejected material expands and cools. Eventually, it will fade from naked eye visibility, leaving behind an expanding shell of gas and either a neutron star or a black hole at its center. If Alnitak leaves behind a neutron star, it will be an object of extraordinary density. A neutron star with the mass of our Sun would have a diameter of only about 20 kilometers. A sugar cube-sized chunk of neutron star material would weigh as much as all of humanity combined. The gravitational field at the surface would be so intense that light itself would be redshifted, losing energy as it climbs out of the gravitational well. Many neutron stars are pulsars, rotating rapidly and beaming radio waves from their magnetic poles. As the neutron star rotates, these beams sweep across space like lighthouse beams.
If Earth happens to lie in the path of one of these beams, we detect regular pulses of radio waves, timed with incredible precision, marking the rotation of the distant neutron star. If Alnitak's core is massive enough, probably above about 3 times the Sun's mass, even neutron degeneracy pressure won't be sufficient to halt the collapse. The core will continue collapsing, shrinking past the neutron star stage, past any point where known physics can stop it. It will collapse down to a black hole, a region where space-time curvature becomes so extreme that not even light can escape. Black holes are among the strangest predictions of general relativity. They are regions defined by an event horizon, a boundary beyond which nothing can return to the outside universe. Anything crossing the event horizon, matter, light, information, is lost to the external universe forever, falling inexorably toward the singularity at the center, where known physics breaks down. We cannot see black holes directly,
but we can detect them through their effects on surrounding matter. Gas falling toward a black hole heats up through friction and compression, emitting X-rays before crossing the event horizon. The gravitational influence of the black hole affects nearby stars, causing them to orbit the invisible companion. These indirect signatures allow astronomers to identify black holes with confidence. Whether Alnitak becomes a neutron star or a black hole depends on the exact mass of its core at the moment of collapse, which in turn depends on how much mass the star has lost through stellar winds during its lifetime, and on the details of the fusion processes in its final days. These details are difficult to predict precisely, so we cannot say with certainty which outcome will occur. But we can say with certainty that one or the other will happen. Alnitak will explode. The explosion will be spectacular.
And the remnant will be either a neutron star or a black hole, both objects representing extreme states of matter and space-time, laboratories for testing physics under conditions impossible to replicate on Earth. Alnilam, the middle star, faces a similar fate, though perhaps on a slightly different timescale. With a mass around 40 times that of the Sun, it is even more massive than Alnitak. It burns its fuel even faster and will reach the end of its life even sooner. Alnilam may have only a few million years remaining, possibly even less. Its tremendous luminosity, 400,000 times that of the Sun, indicates that it is burning fuel at an extraordinary rate. Such profligacy cannot continue indefinitely. The star is living fast and will die young, likely within the next 3 to 5 million years. When Alnilam explodes, it will be an even brighter supernova than Alnitak's explosion, simply because Alnilam is more massive and will release more energy. It might briefly become the brightest object in the night sky aside from the moon, visible during the day as a distinct point of light, perhaps rivaling Venus in brightness. Ancient observers, if humans still exist and are still watching the sky millions of years from now, would surely record such an event with wonder and perhaps fear. A new star appearing where none was before, shining with steady brilliance for weeks or months, would have seemed miraculous or ominous, depending on the culture interpreting it. We, with our scientific understanding, would know it for what it is, the death of a star, violent and spectacular, but entirely natural, entirely predictable within the framework of stellar evolution. We would observe it with telescopes, measuring its spectrum, tracking its light curve, studying the ejected material as it expands outward, learning about the details of supernova physics and nucleosynthesis. Mintaka, the westernmost star, is also destined for a supernova explosion.
As a multiple star system with a combined mass around 50 solar masses, its most massive component will exhaust its fuel and explode, while its companions may survive the explosion, receiving a gravitational kick that might send them speeding through the galaxy as runaway stars. Binary and multiple star systems add complexity to stellar evolution. The stars can exchange mass through gravitational interactions, altering their evolutionary paths. If one star evolves faster and expands into a red giant, its outer layers can be pulled onto its companion, increasing the companion's mass and accelerating its evolution. In some cases, this mass transfer can prevent or delay a supernova explosion. In other cases, it can trigger unusual types of explosions. The details depend on the masses, separation, and evolutionary states of the stars involved, making binary evolution a complex and still not fully understood area of astrophysics. But eventually, the most massive star in the Mintaka system will explode. Like Alnitak and Alnilam, it will enrich the interstellar medium with heavy elements, contribute energy to the surrounding gas, and leave behind a compact remnant. All three belt stars, then, are destined for violent ends.
Within the next 10 million years, and probably within the next few million, they will all have exploded as supernovae. The constellation Orion will look different then. The belt, as we know it, will no longer exist. Other stars will have drifted into view, and new patterns will emerge, named and interpreted by whoever is watching the sky at that time. But the importance of these explosions extends far beyond their visual impact. Supernovae play a crucial role in the chemical evolution of the galaxy and in the cycle of matter that makes life possible. When a massive star explodes, it ejects into space all the heavy elements it created during its lifetime.
The carbon, oxygen, nitrogen, silicon, iron, and many other elements synthesized in the star's core and outer layers are blown outward at tremendous speeds, mixing with the surrounding interstellar gas. Additionally, the supernova explosion itself creates new elements through a process called explosive nucleosynthesis. During the explosion, neutrons are captured by atomic nuclei in rapid succession, building up elements heavier than iron, including gold, platinum, uranium, and many others that cannot be created through normal fusion processes in stellar cores. These heavy elements are essential for the universe we know. Rocky planets like Earth cannot form without silicon, iron, magnesium, and other heavy elements. Life, at least life as we know it, requires carbon, nitrogen, oxygen, phosphorus, and sulfur, along with trace amounts of many other elements. All of these elements were created in stars. Hydrogen and helium and small amounts of lithium and beryllium were produced in the Big Bang. Everything else, every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood, every atom of calcium in your bones was forged in a star and distributed into space by a stellar wind or supernova explosion. This is one of the most profound discoveries of 20th century astronomy, that we are literally made of stars. Our planet, our entire world, were created in the cores of ancient stars billions of years ago. Some of those stars were similar to the belt stars, massive, hot, blue giants that lived fast and died young. Their explosions enriched the gas clouds from which later generations of stars, including our Sun, would form. Without those ancient supernovae, the heavy elements necessary for planets and life would not exist in sufficient quantities. Our own solar system formed from gas that had been enriched by multiple generations of stars.
The molecular cloud from which the Sun and planets condensed 4.5 billion years ago already contained about 2% heavy elements by mass, the products of billions of years of stellar evolution in previous generations. Earth itself is a collection of heavy elements. Its iron core, making up about a third of the planet's mass, came from supernova explosions. The silicon, oxygen, magnesium, and iron in the rocky mantle and crust all were produced in stars. The water in the oceans, the carbon dioxide in the atmosphere, the nitrogen that makes up most of the air, all contain elements forged in stellar cores. When you breathe, you take in oxygen atoms created inside stars that exploded billions of years ago. When you drink water, you incorporate hydrogen from the Big Bang and oxygen from stellar nucleosynthesis. When you eat, you consume carbon, nitrogen, and other elements that cycled through multiple stars, multiple generations of stellar birth and death, before ending up in your food and eventually in your body. This connection is not metaphorical, it is literal and direct. There is no other source for these atoms. They could not have come from anywhere else. You are, quite literally, recycled star material, temporarily organized into a complex structure capable of thought and awareness, destined eventually to return to the cosmos when you die, to be recycled again, perhaps into future stars, planets, or living beings. This perspective can be humbling or exhilarating, depending on how you look at it. On one hand, it emphasizes our smallness, our transience, our insignificance in the vast scope of cosmic time and space. We are temporary, localized, made of borrowed atoms that will eventually return to the cosmic cycle. On the other hand, it connects us intimately to the universe. We are not separate from nature, not alien visitors in a strange and hostile cosmos. We are nature, products of the same processes that created stars and galaxies, participants in the cosmic story, threads in the vast tapestry of existence. The belt stars, when they explode, will continue this process.
The elements they've created will enrich the interstellar medium, mixing with the existing gas, raising the overall heavy element content of that region of the galaxy. Future stars forming from that enriched gas will have higher heavy element content than the belt stars themselves had. This is how the galaxy evolves chemically over billions of years. The first stars, formed from the primordial hydrogen and helium created in the Big Bang, contained almost no heavy elements. They were massive, short-lived, and when they exploded, they seeded the interstellar medium with the first heavy elements. The second generation of stars formed from slightly enriched gas. They too lived, created heavy elements, and returned them to space. The third generation formed from even more enriched gas, and so on, through multiple generations, gradually increasing the heavy element content of the galaxy. Our Sun is a relatively late generation star, formed about 4.5 billion years ago, roughly 9 billion years after the Big Bang. By that time, the galaxy's gas had been enriched by billions of years of stellar evolution, containing enough heavy elements for rocky planets to form. The belt stars, though younger than the Sun, also contain heavy elements inherited from previous generations. When they explode, they'll add to that inheritance, contributing to the ongoing enrichment of the galaxy, making possible the formation of future planets and perhaps future life. This cycle, star formation, stellar evolution, supernova explosion, enrichment of the interstellar medium, new star formation from enriched gas, is the fundamental process by which galaxies evolve. It connects the past, present, and future in a continuous chain, linking the first stars to the latest generation, ensuring that each generation builds on the chemical legacy of those that came before. The Milky Way has been running this cycle for over 13 billion years, since the first stars formed a few 100 million years after the Big Bang. During that time, hundreds of billions of stars have been born, lived, and died.
Each contributed to the enrichment of the galaxy, adding to the pool of heavy elements available for planet formation and life. Each contributed to the enrichment of the galaxy, adding to the pool of heavy elements available for planet formation and life. This process continues today. Stars are forming right now in molecular clouds throughout the galaxy, including in the Orion complex. Some of these newly forming stars will be massive enough to eventually become supernovae themselves, continuing the cycle into the future. The belt stars represent one link in this chain. They formed from enriched gas. They've created new heavy elements through fusion in their cores, and they'll return those elements to the interstellar medium when they explode, making them available for future generations. In this sense, the belt stars are not just objects to observe and study. They're active participants in the galactic ecosystem, playing essential roles in the chemical evolution and ongoing dynamics of the galaxy. The energy they release through radiation and stellar winds affects their surroundings, heating gas, triggering or suppressing star formation, sculpting the structure of molecular clouds. Their eventual supernova explosions will inject enormous amounts of energy into the interstellar medium, creating shock waves that compress gas and trigger new rounds of star formation. This feedback, the influence of massive stars on their environment, is a crucial factor in regulating star formation throughout the galaxy. Without it, star formation would proceed differently, probably more rapidly, and the galaxy would look very different than it does. Massive stars like the belt stars are rare. For every star as massive as Alnitak or Alnilam, there are thousands of stars like our Sun and tens of thousands of smaller red dwarfs. But despite their rarity,
massive stars dominate the energy budget of star-forming regions and have disproportionate influence on galactic evolution. They produce most of the ultraviolet radiation that ionizes hydrogen and creates emission nebulae. They generate most of the heavy elements.
Their stellar winds and supernova explosions inject most of the energy that stirs up the interstellar medium and regulates star formation. In a sense, massive stars are the engines that drive galactic evolution. They're short-lived, burning through their fuel in a few million years. But during those few million years, they shape their environments profoundly, leaving lasting impacts that persist long after they're gone. When the belt stars explode, their supernova remnants will expand outward for tens of thousands of years, gradually slowing as they collide with surrounding gas. These expanding shells will be visible as supernova remnants, glowing shells of hot gas observable in radio waves, X-rays, and optical light. Eventually, after several 100,000 years, the remnants will fade and disperse, merging with the interstellar medium, leaving behind only the compact remnants, neutron stars or black holes, and the enriched gas that marks where the stars once were. Other stars, forming from this enriched gas, will carry forward the chemical legacy of the belt stars. Some of those stars might form planetary systems. Some of those planets might develop conditions suitable for life. And if life does arise on such a planet, it will be made from atoms that once resided in the cores of Alnitak, Alnilam, or Mintaka, forged by fusion, expelled by supernova explosions, incorporated into new worlds. This is the grand cycle of matter in the universe. Nothing is truly created or destroyed, only transformed, recycled, reorganized into new forms. The atoms in your body have been part of many stars, many planets, many living beings over the history of the universe. They'll continue to exist after you die, cycling onward through future stars, planets, and perhaps future life. There's something comforting about this perspective. Death becomes not an end, but a transformation, a return to the cosmic cycle, a contribution to future creation.
Your atoms will go on, participating in processes you'll never witness, becoming part of structures and beings you'll never know. And just as you are made from atoms that cycled through ancient stars, so too will future beings be made from atoms that cycle through you. There's a continuity here, a connection across time, linking all matter in the universe into a single, ongoing process of transformation and renewal. The belt stars are part of this process. They're temporary structures, like all stars, like all planets, like all living things. They'll exist for a certain span of time, contribute to the galactic ecosystem, and then transform into something else. Neutron stars, black holes, expanding clouds of enriched gas, and eventually new stars and planets. Watching them tonight, knowing their future, understanding their role in the cosmic cycle, we can appreciate them not just as beautiful objects, but as active participants in the story that includes us, that explains where we came from and hints at where we're going. There's a poetic symmetry to the fact that we study stars using stars those stars created. The carbon in the proteins of our eyes, the iron in the hemoglobin carrying oxygen to our brains, the calcium in the neurons firing as we think, all were forged in stars. All are now organized into structures capable of understanding the processes that created them. We are the universe examining itself, thinking about itself, understanding itself, and the belt stars, shining steadily across the centuries, provide one of the texts we read in trying to decipher the cosmic story. That story is still being written. The universe is not finished, not static, not complete. It continues to evolve, to create new structures, to explore new possibilities.
Stars are still forming, planets are still being born, life may still be arising in places we haven't yet discovered. The future is open, full of possibilities we can barely imagine. What will happen in 1 billion years, in 10 billion, in 100 billion, when the last stars burn out and the universe grows cold and dark? We don't know.
The far future of the universe depends on properties of dark energy and the expansion rate of space that are still being measured and debated. Current observations suggest the universe will expand forever, galaxies receding from each other, star formation gradually slowing as gas is used up, until eventually, many trillions of years from now, the last stars burn out and only black holes and dead stellar remnants remain. But that future is so distant, so unimaginably far away, that it's difficult to grasp emotionally. For now, for the next billions of years, the universe will remain vibrant, full of stars and galaxies, full of energy and activity, full of processes creating complexity and order. The belt stars will explode long before that distant end. Their explosions will briefly light up the galaxy, visible across thousands of light years, marking the transformation of matter from one form to another, contributing to the ongoing story of cosmic evolution. And perhaps, billions of years from now, a being on a planet orbiting a star formed from the enriched gas of those explosions will look up at their night sky and wonder about the stars they see there. Perhaps they'll develop science and astronomy, learning to read the cosmic story written in starlight, discovering the processes that created them, finding meaning and beauty in the contemplation of their origins. If so, they'll be doing exactly what we're doing now, connecting with the universe through observation and understanding, finding their place in the cosmic story, appreciating the long chain of events that led from the Big Bang through billions of years of stellar evolution to their existence and awareness. This is the gift of consciousness, the blessing and burden of being aware. We can understand the universe, at least partially, at least in the aspects accessible to observation and measurement. And through that understanding, we can appreciate the beauty, complexity, and improbability of our existence. We are not inevitable. The specific arrangement of atoms that makes you, you, that makes me, me, that makes Earth, Earth, none of this was predetermined or necessary.
It's the product of countless contingent events, random fluctuations, chance occurrences, any one of which might have turned out differently, leading to a different outcome. If the molecular cloud that formed our sun had been slightly more or less massive, if the protoplanetary disk had evolved slightly differently, if the asteroid that wiped out the dinosaurs had missed Earth, if any of millions of other events had gone differently, we wouldn't be here. Other beings might exist, or no beings at all, but not us, not in this form, not with these thoughts and experiences. This contingency, this improbability, makes existence all the more precious. We are not guaranteed, not eternal, not inevitable. We are rare, temporary, improbable, and yet here we are, thinking these thoughts, asking these questions, seeking understanding. The belt stars, too, are improbable. The specific arrangement of gas in the Orion molecular cloud that led to their formation, the particular masses and velocities and orbital parameters they ended up with, the chance alignment that makes them appear as a belt from Earth, all of this is contingent, improbable, unique. And yet here they are, shining steadily, following the laws of physics, contributing to the galactic ecosystem, providing us with opportunities to learn and understand. There's something satisfying about the fact that the universe is knowable, that it follows consistent rules, that we can understand those rules through observation and reason. The universe didn't have to be this way. It could have been chaotic, random, impossible to understand. But it's not. It's ordered,
governed by laws, accessible to science. This suggests, perhaps, that the universe is, in some sense, friendly to understanding, conducive to the emergence of consciousness and intelligence. Or perhaps it's simply that we're adapted to the universe we find ourselves in, evolved to perceive and think in ways suited to the particular physics and conditions of our environment. Either way, we find ourselves in a universe we can partially understand, using minds shaped by evolution to comprehend processes that shaped us.
It's a strange loop, a self-referential situation where the universe creates beings capable of understanding the universe, and in understanding, we find meaning. Not meaning imposed from outside, not purpose given by some external authority, but meaning we create through our own awareness, our own appreciation of beauty and complexity, our own sense of connection to the cosmic whole. When you look at Orion's belt tonight, you can choose what meaning to find there. You might see simply 3 bright stars, notable for their arrangement, but not particularly special. You might see the waist of a mythological hunter, a pattern that humans have recognized and named for thousands of years. Or you might see what science reveals, 3 massive suns, hundreds of light years away, each shining with the light of tens of thousands of suns, each racing toward a spectacular death that will enrich the galaxy and contribute to future generations of stars, planets, and perhaps life. You might see your own origins, the processes that created the atoms in your body. You might see the ongoing cosmic cycle of creation and destruction, transformation and renewal. You might see the deep time of the universe, the vast scales of space and energy that dwarf human experience, but that we can comprehend through science and mathematics. All of these perspectives are valid, all add layers of meaning, all enrich the experience of stargazing. The universe revealed by science is not cold or meaningless, but rather full of beauty, wonder, and profound connections that link everything together into a coherent whole. As we reach the end of this exploration, it's worth stepping back and considering what we've learned and what it means. We've traced the properties of 3 stars, Alnitak, Alnilam, and Mintaka, from their positions and distances to their physical characteristics, their histories, and their futures. We've explored the nebulae surrounding them, the processes of star formation occurring in those nebulae, and the role of these stars in the broader galactic ecosystem.
We've learned that these stars, though appearing close together in our sky, are actually separated by hundreds of light years and are not physically connected. We've learned they're all massive, hot, blue supergiants, burning through their fuel at tremendous rates, destined to explode as supernovae within the next few million years. We've learned about the interstellar medium, the gas and dust between stars, and how it serves as both the birthplace and the graveyard of stars. We've learned about the chemical enrichment of the galaxy, the cycle by which heavy elements are created in stellar cores and distributed into space by stellar winds and supernovae explosions. We've connected these processes to our own existence, recognizing that we are made from atoms created in ancient stars, that we are participants in the cosmic cycle, that our origins lie in stellar nucleosynthesis and supernovae explosions billions of years ago. And we've considered the future, both the future of the belt stars, which will explode and transform into neutron stars or black holes, and the far future of the universe, which will continue to evolve for billions or trillions of years before eventually reaching a state we can only speculate about. All of this knowledge comes from science, from careful observation, rigorous measurement, mathematical analysis, and theoretical understanding. It represents the accumulated work of thousands of astronomers over centuries, building on each other's discoveries, refining understanding incrementally, constructing an ever more accurate picture of how the universe works. This is science at its best, revealing truths about the natural world that are stranger and more wonderful than fiction, connecting us to the cosmos, explaining our origins,
and providing a framework for understanding our place in existence. The belt stars will continue to shine, night after night, season after season, year after year, unchanged within human lifetimes, following their predetermined paths toward eventual transformation. They care nothing for our observations, our theories, our interpretations. They simply exist, governed by physics, indifferent to meaning.
But we are not indifferent. We find meaning in understanding them. We connect with them through knowledge, through the realization that we share a common origin, that we are made from the same materials, governed by the same laws, participants in the same cosmic story. This connection is real, grounded in physics and chemistry, not wishful thinking or comforting myth. It's a connection that makes us part of the universe in a deep and literal sense, not separate observers, but integrated participants, threads in the cosmic tapestry. When you look at Orion's belt tonight, remember what you've learned here. Remember the distances, the temperatures, the masses, the futures awaiting these stars. Remember the nebulae, the forming stars, the cycling of matter through stellar birth and death. Remember that you are made from atoms forged in stars, that you are stardust contemplating stars, that you are the universe examining itself. And perhaps in that moment of connection, you'll find what so many have found before, a sense of wonder, of belonging, of profound appreciation for the beauty and complexity of the natural world. Not because the universe was designed for you or cares about you, but because you are capable of understanding it, of appreciating it, of finding meaning in the contemplation of cosmic immensity and your small but significant place within it. This is what astronomy offers, not just knowledge of distant objects, but a perspective that transforms how we see ourselves and our world. It's a gift, freely available to anyone willing to look up at the night sky and wonder what lies beyond. The 3 stars of Orion's belt shine on, as they have for millions of years, as they will for millions more. They are beacons in the darkness, guideposts across the heavens, subjects of endless fascination and study. And in studying them, in understanding them, in connecting with them through science and reason, we become more than isolated individuals on a small planet. We become conscious participants in the cosmic story, aware of our origins, curious about our future, capable of finding beauty and meaning in the contemplation of truths larger than ourselves.
This is the true gift of science. Not just facts and figures, not just theories and equations, but a way of seeing, a perspective that enriches life and deepens appreciation for the extraordinary universe in which we find ourselves. Rest well, knowing that the stars continue their patient journeys through space and time, that the universe unfolds according to natural laws we can understand, that there is beauty and order and meaning to be found in the patient observation and careful reasoning that science embodies. The belt awaits your gaze anytime you wish to reconnect with these distant suns, to remember what they are, to appreciate the long chain of cosmic events that connects them to you across hundreds of light years and billions of years of cosmic history. Sleep peacefully, knowing you are part of something vast and beautiful, something ancient and ongoing, something that began long before you existed and will continue long after you're gone. The grand cosmic story of matter, energy, stars, and consciousness, all woven together into the magnificent tapestry we call the universe.